Hi, everybody. Great pleasure to be here at this very interesting event and to getting these rock star welcomes. So I want to talk about network data, so graphs, and how graphs in subtle ways can leak private information about nodes, about users. And I should preface what I'm going to be talking about by saying that the style of what we're doing here is a bit more theoretical. So we try to posit stochastic models for the problems we're looking at, and we're trying to actually sort of prove fundamental theorems. But don't get your hopes up. There won't be any mathematical proofs today. What I want to focus on is sort of what are the models and what are they telling us, okay? So let me start with a little anecdote that is quite old, more than 12 years ago. In a laudable attempt to help the research community, AOL at the time, which had their own search engine at the time, released a log of search queries. And they anonymized this log, of course. So they had these random IDs that they attributed to users. So anonymized user IDs. So you know, what could possibly go wrong? Well, you might guess it, you might remember this story even, but it went wrong very quickly. The New York Times actually quickly uncovered one of these users. And you know, in hindsight, this is pretty obvious, right? You look at sort of locations that someone is looking for, and maybe a name, and quickly that's enough to de-anonymize. And the New York Times found this elderly lady in Lilburn, Georgia, and she was willing to come on the record. And AOL defended themselves by saying there was no personally identifiable data provided by AOL with those records, but search queries themselves can sometimes include such information. And that was the problem. And the CTO of AOL at the time, as a result of this anecdote, decided to spend more time with her family. So these things have consequences. And so I want to talk about similar problems, similar issues like this, but in the context of graphs or networks. And so network data, of course, is you know, critical in many important machine learning and social network analytics tasks. So for example, you know, we can use them to detect communities in networks. We can model epidemics, how influence flows through a network, or how to optimize for influence by influencing specific nodes or infecting specific nodes. We can think about traffic flows and how to optimize them. We can predict where the next links are going to appear, you know, who are people you might know on LinkedIn and Facebook, and so on. So there's a rich set of these problems. So network and graph data is very central. And so a key research question is, so if we have a large network, can we just anonymize it and then release it into the wild? What could possibly go wrong? So that's the question that we want to really address today. And I want to give you today two sort of relatively subtle attacks that one can execute on such an anonymized network to get back the de-anonymized network, and thereby leaking private information. So in the first attack, we take a network and we sort of make two copies of it. And you look at this and it's sort of obvious that it's the same network, but let me confuse you and turn this around. And now if I had started with this, it would already be quite difficult to see that this is actually, that these are isomorphic graphs. So how would you go about de-anonymizing, if you had one of these networks in a anonymized state and then another network that you get from another source, how would you go about re-identifying the nodes on this one? So one thing, in a fairly well-known paper, Shmatikov and Narayan did this in 2009, where they created heuristics that got this task done, that basically re-identified the nodes, found the correct node correspondences between these two networks. And the way they did this, they first sort of tried to find nodes that stick out, that are special. So typically high-degree nodes. In one network, and then also in the other network, and then you can sort of start out by trying to match these up, and gives you a starting bijection to work with, right? And then, of course, one question is how do you map them correctly, these special nodes? And then, more generally, we don't want to assume that we have two isomorphic graphs. That's too easy. Well, not the graph isomorphism is easy at all, but for practical networks, it tends to be easy. But we assume there's noise, right? We get side information that is just a noisy version of the real network. And so they developed these heuristics where, as I said, they started with these special nodes, like seed nodes, and then they tried to propagate out the map from these seed nodes. So they had sort of heuristics that said, these two green nodes would be better candidates for a new linkage map than these two orange ones, because the green node is neighbor with the same two already mapped nodes as here. And so basically with such heuristics, this map can essentially propagate in sort of a recursive fashion. And using this very simple heuristics, they managed to actually de-anonymize social networks with millions of nodes. It's quite remarkable and scary if you're concerned about network privacy. And fundamental questions are, when does this work? And in what sense does it depend on the graph properties? And the question we attacked here is sort of to say, okay, rather than looking at some special heuristics, can we say something fundamental about what an infinitely powerful adversary can or cannot do with these networks? So to define the problem, so we have an anonymized network, we have side information that is a noisy copy of this, and the question is, if we sort of anonymize these two, can we find the correct mapping between the two vertex sets in these two graphs? So for this, we need to postulate a model, and the model we use is the Erdős-Renyi random graph. You have n nodes. Every possible pair of nodes, you flip an independent coin with probability p, there's an edge. Probability 1 minus p, there is no edge. It's about the simplest probabilistic model for a graph you can think of. It has been studied since the 1950s, exhaustively in probability and math. And it's about the simplest model for which we can hope to actually have formal proofs of de-anonymizability. And so we need a model for two graphs, right? And so what we do is we assume that there's an underlying unknown or invisible true network. Think of this as a true social network between a bunch of people. And then we flip two coins for each edge independently with probability S to say there's an edge in the left network and there's an edge in the right network. And this way we generate two basically correlated, two correlated networks. Now we have a model, and now we can try to prove something for this model. And this parameter S node measures the similarity of the two networks. So if S is 1, they're isomorphic. If S is small, they're quite different from each other. And so, as I said, no proofs. I jumped directly to results. But so, thanks to models like this, we can actually show something. And what I show you here is how the average degree of the two visible graphs can or has to scale so that an infinitely powerful adversary can crack the anonymization, where you're not safe, releasing the data. And what I wanted to draw your attention on here is that the condition is quite weak. So so n is the network size, and the dependence on network size is quite benign, just log n. And also the benefit in terms of maintaining privacy of the similarity parameter S is actually not very strong. It's only quadratic. You'd hope that maybe it would be exponential or a phase transition, but it's not. So even if correlation is relatively weak, privacy is not strong. Good, so or bad, depends on your point of view. So let me shift gears. We also have done work on sort of the computational aspect of this that resembles the Narayan-Shmatikov approach, but again on this random graph model so that you can prove something. So I again have my two graphs here and here, and we assume that we have an initial set of matched pairs, and now I want to map the rest. So basically compute all the other correspondences. And basically, we look at about the simplest possible algorithm that basically does this. It's a recursive rule where we just say, if a pair of nodes are neighbors in both networks, then we match them too. And then you apply this rule recursively. And when you do this, you sometimes get correct matches, but you can also get some matching errors. So the process might percolate, but it might match up the wrong pairs. And so there is a trade-off. If you make the number of neighbors you want before you match large, you minimize the probability of this kind of matching error, but the process might not percolate. And if R is small, the process is very likely to percolate. So there's a trade-off, and to understand this trade-off, we basically use tools that are similar to understanding why a sponge can hold water. So it's a tool from statistical physics called percolation theory that we can apply to this kind of problem to basically show when this process percolates and percolates correctly. And again, we get results of this type on, and so basically there's a condition on the size of this seed set here. So if this seed set is even just a little bit larger than a critical threshold AC, a little bit larger, then the process percolates and matches up the two graphs almost perfectly. And if we're slightly below, it doesn't. So it's essentially a phase transition type phenomenon like you know from physics. And lo and behold, in their original paper by Narayan and Shmatikov, they have this plot where experimentally the success rate in percent here jumps very brutally as they increase the number of seeds from essentially 0 to pretty good, and then doesn't get much better. So our model can actually explain this and sort of give guidelines of when this process is likely to succeed and when not. Good. So now, let's make it harder. So far we had one full network, and we tried to de-anonymize it with another, with side information that's correlated with the original network. And this is inspired by actually an actual anonymization procedure that was used in a particular data challenge, the Orange Data for Development Challenge a few years ago. And what they wanted to release a social network, essentially people SMSing and phoning each other over millions of inhabitants of Ivory Coast. And they were concerned about people de-anonymizing this network. And so what they did is they said, we're not going to release the whole network, we're going to release many little pieces, many small subgraphs. In effect, the 2 ego net, so 2 hops around every user, but you didn't know that this user here might be that user there. They're like independent networks. So the same question arises, right? So if I take a big network that I want to anonymize, and what I do is I take a small subgraph around every node. So let's make it even harder. We just take 1 hop out and the crosslinks, right? So the blue node here has these 3 neighbors and this crosslink. And I generate all of these subgraphs, n subgraphs. And now I anonymize them. So it looks like this. Is it possible to get back the original network from these little pieces, even though you don't know that this node is that node? Okay? So this seems hard at first. And so more formally, so we have a ground truth network. We get all these little subgraphs, or we call them, patches. Can we get back an estimate of the original graph that is isomorphic to the original? So here the proof or the approach is actually algorithmic. So I'm going to describe to you a scheme that we use to try to reconstruct this graph. And it relies on a fairly subtle observation, which is that, so look at 2 overlapping such subgraphs, the one centered at U and the one centered at V. And suppose that the V is a neighbor of U, so V occurs in the patch, in U's patch, and U occurs in V's patch. Now look at the common neighbors of U and V. So these 3 red nodes. These 3 red nodes and edges among these, by definition, occur in both of these patches, right? So these are subgraphs or both of these subgraphs, subgraphs. So you'll find this subgraph here and you find this subgraph here. So at the beginning, you don't know that this node is V and that this node is U, right? But if these 2 subgraphs here are unique network-wide, then this can only be V and this can only be U. And that's what algorithmically you can exploit to sort of gradually rebuilding the network. So if you have these 3 patches, you would get this, right? So if these 2 are unique globally and these 2 are unique globally, then the only possible constellation is this. And so as you do this recursively, you rebuild the whole network. And so these common neighbor subgraphs act essentially like a fingerprint for the relevant edge. So here the edge UV, here the edge UW. So it's kind of like putting back together a puzzle where these fingerprint subgraphs represent the pieces of the puzzle that click together, and you're trying to put together the whole puzzle. So we can show that, well, first of all, now with a GNP graph, this doesn't work, except if it's extremely dense. And the reason is, to get meaningful fingerprints, you need clustering or transitivity in the network. You need lots of triangles, which the GNP doesn't have because it locally looks like a tree, but real networks definitely do have that. They do have transitivity. Friends of friends are often friends. And so, again, sort of skipping over the exact form of the result, what is, again, remarkable here is that the conditions for this reconstruction process to work are fairly benign. In particular, the average degree of the network only needs to grow as log square n in the size of the network. And so under these cryptic conditions here, but as I said, they're not too strong, this recursive reconstruction process I just walked you through will succeed perfectly with high probability. And again, we have reconstructed, we have broken the anonymization scheme quite easily. So, to wrap up, I've shown you two results. I've shown you network alignment, which is essentially, at the base of it, an extremely large-scale combinatorial problem. There's n factorial possible bijections to try between these two graphs. Nevertheless, with relatively simple heuristics over most graphs, this is actually relatively easy. And if it's easy for random graphs, it's certainly going to be easy for real networks, because random graphs, in a sense, are very uniform. Every pair of edges has the same probability of existing. Real networks have much stronger features. They have, skewed degree distributions, they have communities and so on. All of that makes the problem even easier. And then I showed you assembly, where we try to assemble the big network from many small networks. And here too, this is actually, for most graphs, relatively easy, with the additional requirement that the graph should be relatively transitive or have triangles, which again is true for most real networks. So the lesson is beware of statistical attacks and of subtle ways in which anonymized privacy is different from anonymization. Just removing identifiers does not do the trick. And the holy grail here, of course, would be approaches where we can provably defend the privacy while having still utility. So where we can ask queries about the graph, about distances, about density, about edges, about communities, while provably defending against all possible such attacks. And this holy grail is still out there to be captured. Thank you very much. I'm happy to take questions.
Thank you, Matthias. I still haven't received any questions, but I still have one. Have any of these statistical attacks already happened? Or if I'm really a bad guy, if I were a bad guy right now, can I use this, what I have just seen, to do an attack?
Yes, so on the so these things do work on real data. I didn't have time to show it because I wanted to sort of focus on the fundamental results, but this works very well on real data. So on the orange data set, the rules of the data challenge explicitly forbade us to try to de-anonymize. So we did not try it there, but we did it for many other real network data sets out there, like from the SNAP repository, for example. Mm-hmm. So yes, this works in practice.
And aren't you afraid that, because it's now public, this research, kind of, that there will be guys trying even more to...
That's the risk, but I think it's always more important to alert the good guys about the risks than sort of withhold, possible attacks from the bad guys. I think in the end, that's the right approach to go towards provable privacy guarantees rather than intuitive privacy guarantees.
And who is the potential object of attack today?
Well, I mean, any social network. Any scrapable social network could be a victim. Let me also point out that these approaches also have positive applications. So we have, for example, on the first problem, applied these algorithms to biological data. So in biology, there are networks that describe sort of how a cell functions. The protein-protein interaction network says which proteins in a cell can interact with each other. And these resemble each other from species to species. So if you manage to match them, it sort of tells you this protein in the mouse corresponds to this in a human, and of course there's obvious benefits. And so with our algorithms, we were actually able to outperform previous approaches to do this. So it's not only about privacy, and that's
wow, it's interesting. And we have received already some questions. What is the preferred method for publishing anonymized data?
Oh, that's a loaded question. Well, the preferred method, I don't know. I don't know of a method for graph data specifically that would guarantee that with the right side information you can't crack it. So quite honestly, I don't know. I don't know how to do this.
And would zero-knowledge proofs over the graph help to maintain privacy?
Yes, I'm aware of that. There's been work in that direction. I'm not completely up to date on the latest. From what I've seen is that usually you have to essentially remove so much information from the data that you have provable privacy, but utility is essentially also gone. Mm-hmm. That is my understanding of the state of the art, but it's a very interesting approach.
I think we can still manage one. There is still the question, could you please give more examples in real world for these attacks?
More examples in the real world for these attacks. So for example, in follow-up work, again by Narayan and Shmatikov, they actually won a data challenge. I think it was on the recommender systems. Uh-huh. So it was a data challenge where one had to develop recommender systems to basically say, this movie would have been liked, would have been given 4-star by this person and 2 stars by that person. And instead what they did, they used these kinds of approaches to de-anonymize the data set, where then they just had the ground truth. And then the question was that allowed by the rules? And there was nothing in the rules that forbade it, and they won the data challenge, even though they absolutely didn't work on recommender systems, but de-anonymized. So this was not a disaster. It was just an interesting anecdote again. But so just to re-emphasize that these risks are everywhere, not just in these, let's say, slightly idealized mathematical models for graphs.
Thank you, Matthias. This was brilliant. Thank you.
Thanks very much.